A strict sense stationary and a wide sense stationary. What they actually means is a strict sense stationary, a random process x of t is called strict sense stationary if its statistics are invariant to a shift of origin. The process x of t is SSS if the function x of 1 up to x of n. Okay, these could be the outcomes for a time instant t1 to tn will be equals to f of x, x1 to xn, but there is a shift in the origin with t1 plus c to tn plus c. Thus, this shift does not impact a strict sense stationary function. However, a wide sense stationary is a process which is not stationary in strict sense but have a constant mean value and an autocorrelation function that are independent of the origin. What we mean by mean value is that its expectation of WSS random process is given or is calculated by this formula. An autocorrelation function is calculated by this formula. Autocorrelation function is the multiplication of signal itself from its time shifted function. X of t is being multiplied with x of t, only the difference is in the origin. Calculating the time average, mean and autocorrelation. In communication, we usually take those signals whose time average mean is equals to ensemble mean. That means if we calculate mathematically, then also its mean is same, and if we take its time average, then also its mean is same and equal to the ensemble mean. Here I have shown you the mathematical formula for a random signal. X for a random process x of t, limit t tends to infinity from minus t by 2 to t by 2 x of t dt. Our x t1 comma t2 is limit t tends to infinity from minus t by 2 to t by 2 xt plus tau dt. Here the ensemble mean should be equal to the time average mean. What we calculate in communication is mu of x. Expectation of that mean value will give me expectation of the time average mean is limit t tends to infinity minus t by 2 to t by 2 expectation of x of t dt. This expectation of x, if calculated mathematically, will give me x of x into p of x, that is outcome into probability of outcome. That will be equals to mu of x. And this is the value that we calculate to get our mean in communication. X bar is the DC level of the signal that remains constant. Moving on. What actually an ergodic random process is? Ergodic random process are those whose time average are same for all the sample functions and equal to the corresponding ensemble averages. What we mean is that suppose there is x of x of t is equals to a and a cos function, where a is a random variable. So for any instant, if we calculate x1 of t, then a could have a1 value, a2 value, and okay, yeah. So a could have a1 value, a2 value, and so on. Thus, it won't be having the same ensemble mean as that of time average. We calculate it from minus infinity to plus infinity. Thus, in such scenarios, it won't be a random process. Okay, this is the property which has to be followed by a random process. A stationary x of t is called ergodic if its mean x bar, which is time average, is equals to mu of x, that is ensemble average. We can see that a random process, if from this graph we can actually see the random process, the white sands stationary process, the stationary process, and the ergodic process. Ergodic process can be a stationary process too, a white sands stationary process too, and a random process. However, a strict sense stationary can be a white sands stationary, but the reverse is not possible. Moving on, the autocorrelation of WSS signal. Here I have tried to resolve first the mean of a WSS signal, and then we can calculate, then we have calculated the autocorrelation function. So you can pause the video and look how this been performed mathematically to have a better understanding of WSS signal. This is actually the autocorrelation function. If here the a and a square would have been a random variable, then this process won't be a random process. However, in this scenario, a is a constant, then we can take it as a constant, and the Rx t1 and t2 value is equals to a square by 2 cos omega ct tau, where tau is the time difference. Moving on to the properties of correlation, that is autocorrelation and cross correlation. There are three main properties which you can see on the slides. We always take Rx tau to be an even function. Then its property Rx tau will be equals to Rx minus tau. Rx tau will be less than Rx 0, and Rx 0 is equals to x square. Similarly for cross correlation. To calculating power spectral density is an important property in communication. Power spectral density is calculated in frequency domain. This was derived from Wernicke-Inchin theorem, that if we do a Fourier transform of R of t, we'll get power spectral density, and if we take the Fourier transform of S of x, we'll get the autocorrelation function. In frequency domain, to calculate with the help of mathematical tool, we can calculate it with this formula. And to calculate in time domain with the help of power spectral density, we can calculate in this form. For Rx of 0 is e into x square of t. Okay, which is 1 upon 2 pi from minus infinity to plus infinity, which will be plus. Yeah, it is plus. It's not able to be seen, but it is plus. From SWDW. Here I have shown you a gate example. Please go through this and pause this video over here. Else I have illustrated the solution for this video in this slide. There is one correction over here. It should be plus, as we can see that if we multiply minus of xt minus t naught to minus of xt minus t naught minus tau, it will give the minus minus will give me a plus. So it should be a plus over here and plus over here. Okay, so yeah, it is a plus in this video. Moving forward, I have given you one more example from the gate examination. You can solve this and you can get the link of it in the below slide, the solution for it in the links provided. Let's go to the next topic, that's noise.